Okay, so I'm going to start with a brief recap on NVMe. We've had quite a few material in the conference. I'll jump over that very quickly. Talk a little bit about the Linux target driver and how an offload scheme might integrate with it. And then finally go over a verb's proposal for offloading NVMe. NVMe-over-Fabric, sorry. So first of all, as you all know, NVMe is a PCIe standard. Provides very efficient access to storage controllers through the PCI. It's very minimalistic, very efficient. Essentially, the way that host software operates with it is through pairs of submission and completion queues that are directly accessed from software. The queues reside in memory, and the only thing that needs to be done on the I/O path is just ring a doorbell, and you're set. People from this community should be quite familiar with this concept of a pair of queues and ringing doorbells. So the focus of NVMe is efficiency and scalability. The command set is optimized for small transfers, just 64 bytes of a command. Completions are small, and the mandatory command set is small. And it supports MSIX, which means that you can scale across the cores, etc. The problem is that NVMe alone currently constrains you to the box, either within a single server or storage systems. And when you look for solutions for doing scale-out storage, all of these current technologies like PCI-attached devices, SAS, SATA, don't cut it. Another option is iSCSI or FCOE, which have their own, they're more complex architectures. And what NVMe-over-Fabric plans to do is basically to extend the simplicity and efficiency of the local NVMe to fabrics. So the goal is to have a simple scale-out without any protocol processing, using the same command sets, and add as minimal latency as possible to what you can achieve with the local drive. When you look at how the standard was defined, basically they defined a mapping between fabric queues, which are for example, RDMA, QPs, to the concepts of NVMe. So for example, if on an NVMe device you posted a new submission entry to the submit queue, in NVMe-over-Fabric you do the same thing by sending a command in a capsule that we'll get in a moment on a QP send queue. If on the local device you pull the completion queue in memory, then here the equivalent is pulling the receive CQ and inspecting a completed receivable key on the RDMA device. In terms of how this is operated, so in the NVMe case, the host writes a submission queue entry and rings a doorbell. And in the NVMe-over-Fabric, it writes the same NVMe command, but it carries it invokes the transfer by submitting a wookie to the RDMA send queue. And same goes for completions. In the NVMe case, software detects a completion in memory on the completion queue, possibly waiting first for an interrupt. And in NVMe-oF, you get command responses just as receive messages, and then you pull the receive CQ. In terms of data exchange, a local drive has two formats, physical pages or a scatter-gather list. In Fabrics, you use either inline data or RDMA reads and writes that are invoked by the target, very similar to other storage protocols. In terms of how commands are processed, the NVMe-oF standard basically keeps this basic minimal command unmodified. and it extends it into a so-called capsule that carries both the command and a little bit of additional data. This additional data can either be a scatter-gather list. So in contrast to the local NVMe where you fetch a scatter-gather list from memory, here additional scatter-gather entries are carried in the capsule. Or you do RDMA, reads and writes to fetch the data. In terms of response, again, this is the standard NVMe response. And in some cases or in some transports, you can have additional data. When we look at how an NVMe-oF target is implemented, this is a high-level diagram of what's happening in Linux. You have here the NVMe-oF target driver. It sits atop of an RDMA NIC. You have hosts connecting to it. So this whole thing is your NVMe-oF subsystem. Each host that establishes an RDMA connection to the admin queue essentially forms an association with the controller and submits commands. The way the target implements these or handles the commands is basically it uses the block layer to submit block IO operations to conduct the operation. So one thing to note, of course, that this whole host acts as an NVMe-oF subsystem, but it doesn't mean that it's necessarily talking with NVMe drives as the way to store the actual data. In fact, any Linux block device can serve as an NVMe namespace in this NVMe-oF subsystem. So what comes to mind is that since we have here a well-defined standard of accessing NVMe over the PCI, across the fabrics, and we have another specification that specifies how to access pairs of queues in an NVMe local device, and everything here is so nicely standard, maybe we can, instead of going through the host here and having software layers that emulate this access. Of course, there is an advantage of emulating access. For example, as I said, you can use the NVMe-oF subsystem here to all types of storage. But in the case that this storage is actually an NVMe device, this path could be done in hardware in a very straightforward and a standard manner. So this is what NVMe-off acceleration is all about. Let's call it an accelerated NVMe-oF target driver would do as follows. It would obtain the properties of an IO queue and a submission queue and a completion queue from an underlying NVMe device. It would then bind a queue pair to that NVMe device. So once that binding is done, the actual data transfers can be done in hardware directly between the RDMA NIC and the NVMe backend device. So it looks something like this. We'll talk here about a read transaction. So in this case, we have an incoming request. And from here, what's going to happen is that we post the read request to the NVMe submission queue. After that, we ring the NVMe doorbell. Now, the NVMe device starts its own working, its own processing. It reads the command, processes it, and writes the data. And after the data is written to the memory, it fills in a completion entry. And that's where the NIC can pull that completion entry and now initiate an RDMA write that transfers that data to the originating host. And of course, finally, sending the response that the IO operation is completed. In the case where we use a controller memory buffer, we don't even need to use the host memory at all. So the control memory buffer can be used to stage the data that's being generated by the NVMe device. It could either be an NVMe controller buffer, or it could be device memory, as we saw in the last slide, in the last presentation. So we want to introduce a programmatic way to implement this concept, and we came up with the following model. Essentially, we want to have a representation of a subsystem which aggregates a bunch of connections from remote hosts identified by RCQPs. And this subsystem is associated with one or more backend NVMe controllers. And this association, when we looked for an object to do that, we thought that doing subclassing the SRQ sounded like a good option because it already aggregates a lot of incoming connections. So we have this that's called the NVMe SRQ. It aggregates a bunch of QPs from above, and then we have some representation of the backend devices, which represent an IO submit queue and completion queue pair on the backend controller. This queue, kind of like the XRC queue, has its own receive completion queue. Rather than using the individual receive queues of each of the queue pairs. So in this case, it's kind of like XRC. OK, so now let's see how these components work together. So first of all, when you're offloading such transactions, the actual offloaded commands are not visible to software. It means that offload commands don't generate receive completions on that SRQ completion and completion queue. It doesn't consume receive wikis that are posted by software. The offload doesn't consume space on the individual connection send queues when sending responses, and it doesn't generate any send completions. So when I go back to the model, whenever you're offloading stuff, the association with the SRQ is used to do this kind of association between these basic objects. But there are commands that you don't offload. Maybe new stuff that's coming up, maybe commands that are not supported today. And in that case, you fall into the standard processing that's defined by verbs. And that means that any non-offloaded command that comes in from one of these connections just generates an SRQ completion normally. And when you want to send responses in software, you just post them normally on the send queue of the individual connections. Another thing to note here is that the backend IO queue and the completion queue are under exclusive ownership of the hardware. So again, we're transferring the ownership of this specific queue to the hardware. So if I have a scenario where I'm doing a software fallback, and I want to invoke some operation on the NVMe device, I'm going to use another IO queue. By the way, here I put in a single submission queue on this backend controller. But of course, you could have a lot of these. The decision here is primarily a performance decision according to the capabilities of the NVMe backend device. If it can handle the full bandwidth with a single queue, that's fine. If it needs more queues, then we can support that as well. A final thing to note is that front-end namespaces are not necessarily equal to back-end namespaces. So again, if I'm going back to the model here, or even back to the Linux model, so there's no one-to-one relationship between the NVMe-oF subsystem that I'm presenting to my clients and the local NVMe drives. I can aggregate a lot of namespaces from different devices, whether they're NVMe devices or other types of storage. And the same thing is likely to happen in the offload case. So I think today NVMe devices, they have multiple queues, but usually they're in the order of the number of cores of the machine, like 32 or 64 queues. They are not in the order of 64,000 like the spec defines. And people are not going to assume that you have like one-to-one correspondence between a queue pair and an NVMe submission queue. So we need some kind of multiplexing being done in the offload as well. So that's the last bullet here. So if we look at how this is being implemented in verbs, so you start with querying the device, whether it has NVMe offload. Then you proceed with a representation of the NVMe subsystem, which, as I said, is a subclass of an SRQ. You create backend objects which correspond to submission queues and completion queues of the backend NVMe devices. Then you have to map namespaces. So, for example, a front-end namespace ID 2 could be mapped to a backend namespace ID 10 on a given NVMe backend controller. Once you have that, you can basically add in QPs that are connected through the RDMA same as usual. And the final step is to enable acceleration. Now, the NVMe spec defines that I/O operations cannot be started in a connection prior to completing the connection. So software has control when to enable the actual acceleration. Until it enables acceleration, the QP behaves exactly like it would with any association to an SRQ. Let's look a little bit at these APIs in more detail. The first thing I want to note is the representation of the subsystem, which is the NVMe SRQ. The parameters that you have here at the device level, we have an offload type, which basically is an enumeration of operations that can be offloaded. The total backend controllers is device-wide. The max backend controllers is the amount of controllers I can tie into a single SRQ. This is the max namespaces namespace mappings that I can do. As we've seen, if we're not using controller memory buffers, we need to allocate some kind of staging memory to basically do the transactions between the NVMe device and the RDMA device. So we have your capabilities of the min and max buffer pages that the device can handle, the maximum transaction size, min and max for the queue sizes, and finally, we have the in-capsule data offset that the system needs, and or the maximum, and the control capsule size, the command capsule size. When you're creating a specific SRQ, you select something that has to adhere to those capabilities, providing more or less the same stuff, but here it's on min and max, it's the exact size that you want to open, and you provide the staging buffer as a memory key and an address and length. So this is going to be the buffer that the device uses. Now about the backends. So we need a way to represent a backend NVMe device to the RDMA controller. And we do that using this new structure here, where we have mappings of the submission queue, the completion queue, the doorbells, maybe some non-zero initial value if you're binding later on, a timeout value, and some complex for future extensions. The one thing that I do want to comment here is that all these memory representations we're providing as a scatter-gather list that has an R key in it, has a memory key in it, a memory key in it. And the idea is that probably the memory buffers are pretty straightforward. You just allocate memory and register a memory region. In terms of mapping the doorbell of a pure NVMe device, we need a way to do that. I've looked at the latest SPDK information. I saw that there was some experimental APIs to enable peer-to-peer traffic. We'll probably need something here, but in any case, it's not specific to this API. So right now, we assume that the user somehow obtained a memory region that maps the doorbells of the NVMe device. Now we're going to talk about the actual association. So just two simple calls that once you have that structure filled out, you can create an NVMe control. You specify the SRQ, which represents the NVMe front end. And now the hardware knows how to drive that IO submission queue and completion queue. The final stage is mapping namespaces. So what we want to do, we want to map a front-end namespace ID into a specific controller and that specific controller's namespace ID. And in addition to that, we want to provide some idea about the LBA data size. So the hardware would know how to allocate buffers according to the request, since everything is given in LBA units. So we have here the NVMe control object, the front-end NSID, the back-end NSID, and the LBA size. And after you map that on the given SRQ, you're done. The final thing that we need to do is enable acceleration. And as I said before, this could happen after the QP was created and even after the QP has sent traffic, because the connect request after that you might want to do authentication, is something that's done by software. And only after you fully complete the connect procedure, you want to start offloading IO requests. So this is what we're going to do with a new modified QP that basically enables acceleration on the accelerated QP. Okay, exception errors cases. So during processing, there could be several sources of errors or exceptions. The first is just RDMA transport errors, like retry exceeded. Whenever such a transport error occurs on an offloaded QP, the QP is going to transition into an error state and generate the fatal async event. The reason for that, rather than using flushed Wookiee errors, is because that the offloaded Wookiees and cookies are not visible to software. So it could be the case that for a long time, software didn't need to get involved, something happened, and there's simply no work request to flush and inform the error, so we're using an asynchronous error for that. The second source of error could be because of interaction with the backend NVMe device. For example, let's say that the HCA tries to read something from memory, for example, do the completion, pull memory for an NVMe completion, and from some reason I get a PCI timeout on that reads. So in this case, I need to report it. It's not a transport error, but it still stops me from continuing this processing. So in these cases, we're generating a new kind of error that are specific to the backend controller. And these errors are either a PCI error or just a timeout that some request that I submitted to the NVMe backend didn't get any response for a very large time, and I want software to take control. In terms of the status of this work, so there was initial RFC submitted on the list. It covers all these, basically what I've presented here. There's man pages and all the code changes in this RFC, so we're soliciting feedback on that. This is all currently user space verbs for implementing user space storage controllers using SPDK or using other other frameworks. In terms of kernel offloads, discussions are still ongoing. One of the issues is a question whether can we share an NVMe controller between the offload and NVMe-over-Fabrics and a local NVMe block device. And there are pros and there are cons. The cons are mostly according to handling errors correctly. It could be that one possible solution would be to use a separate NVMe controller for the fabrics than the one that's used by the host. Still on the same NVMe subsystems, this would require SRIOV-capable NVMe devices which have more than one controller. So you can still share a namespace between the fabrics and the local host, but you would need two controllers to provide this acceleration in parallel to local processing. And that's it.
Okay, so when a command arrives, how do you choose which MR you are going to use to save the data on the host before writing it back or reading it from the NVMe controller?
Mm-hmm. So when you establish the offload context, you provide staging memory, and from that time onwards, it's just here it is. So when you right here, you provide the memory key. It's dead. Okay. You provide memory key and the address and length of memory that you want the device to use as staging. But once you do that, this buffer is under device ownership.
And it's common for all the QPs that will be offloaded? That's the device is managing it?
The device is managing it, and it uses it for all the Q pairs that are associated with the same SRQ.
Okay. And so that's just a large memory that's and if something arrives and you don't have any more memory for it, I mean, how do you make sure that you're not using too many QPs or the SQ depth is too long so you won't have a memory to save it in?
So the device is in charge of that. When it comes in, it gets requests. If it has available staging buffers, it will start pulling in the data. Again, depending if it's read or write, or reserving data for read responses, right? If not, it's just gonna pause processing until some staging buffer frees up.
And is there a way to ask for the SQ size to be limited to a certain size for that to?
Yeah. In the attributes here, you specify all the sizes that you need.
Okay, and just one more question. That's supposed to work with IOMMU? I mean, how this buffer does, when you give the NVMe the command, can you give the physical address that was mapped for that specific RNIC, and it should work on the same? So
there are two cases here for peer-to-peer traffic. I'd say in the slides that are presented here, the common use case is that you're using the host buffers as staging. So there you don't need any IOMMU for peer-to-peer traffic, but you do need peer-to-peer traffic for the doorbells.
Yeah. But so you're expecting it not to work with IOMMU on the host? Or would it work if you would have IOMMU? Because the addressing would look different if you're looking from the NVMe controller and the RNIC.
Right. So for example, let's take an SPDK application that has some VFIO NVMe device passed through and an RDMA device which is not VFIO. So for the RDMA device, you operate it normally. For the VFIO device, you would need a way to register a memory region on its controller. So we'll need some kind of support in the kernel that when you have this register operation on this NVMe device on its bar, we can have a memory key that maps directly into that, into the DMA addresses. In this case, I think the actual DMA access does require an MMU because the NIC is not passed through, so it doesn't use an MMU unless you're applying MMU for all your operations.
Okay, thanks.
Yeah.
I have a question. So is this to support a more Mellanox kind of specific offload capability, or is it a more generic thing? Because kind of what I'm trying to figure out is why you're going through verbs to do this stuff, to set up things on, perhaps a proprietary offload solution, and is that the right way to do it? And then the other kind of follow-up question is, if you were going to have some capability for setting up various offload capabilities, would it make more sense to do it in a standard way through the NVM Express consortium rather than through the OpenFabrics side of the world?
Okay, so first of all, in terms of the offload itself, nothing here is proprietary. I mean, when you look at how an NVMe frontend needs to process an NVMe request, it's completely covered by the standards what you need to do. So on that front, nothing here is implementation specific.
Well,
In terms of why you need it through verbs, is because we don't want to do all the thing in hardware. We want most of the management to remain in software. Possibly, if we're going to push it in the kernel, of course, we want to reuse the existing NVMe-oF Target to manage all that.
To me, this seems like it's kind of a hybrid. It's not completely offloaded because it's like you're still having this offloaded device plugged into a server where there's software above it as well, right? And that's where I think that maybe there might be other people doing targets in the industry that are not plugged into any host. It's all maybe in an FPGA or something. So
Could be. Well,
that's why I'm trying to figure out if this is more of a, well, this is your solution, but should we be doing it, making it look like it's, you know, a solution for everybody by putting it in through IB verbs?
Well,
So
first of all,
that's
it's not a solution. It's just a means to offload from one queue to another queue according to a standard. So in terms of if anybody wants to implement it, they can implement it. As you see, there's nothing here in terms of concepts that prevents anyone else from implementing it.
Yeah.
In terms of software fallback, it's very common practice in a lot of things. For example, let's say you have an IPsec offload and you can't handle IP fragments, and then you fall back to software to handle the fragments. I mean, there are a lot of, these hybrid approach to systems is usually the way that you handle 99% of your fast path in hardware, and you let software deal with all of the exceptions.
Yeah, you know, to my other point, I'm just kind of wondering if it might make sense to try and go through the standards committee and do something that's, you know, a ratified standard through NVM Express Consortium for this type of capability rather than doing something that, you know, in Linux it's kind of a, hopefully a semi-de facto standard, but not really something that's been agreed to by all the various, you know, people that are building NVMe targets and things like that. So anyway, that's just something to think about.
Yeah.
Can I slip in two quick questions before we're done? One is the subsystem, the NVMe subsystem. How many hosts are you expecting to be able to connect to that? Is it more than one?
Incoming host? No. As many as you have QPs, millions.
So each subsystem defines a single set of bounce buffers, which would mean you'd be mixing bounce buffers. You know, the host A's would use bounce buffers out of the same pool as host B, which seems like it could be a security issue. Yeah, host A maybe doesn't want bounce buffers that were recently used by host B.
Why not? It's not exposed to the host.
No? Okay, so as long as there's no leak or no way to get hold of my secret key that was just in that bounce buffer and now still in that bounce buffer, but now we're using that, we've allocated that to a different host. It doesn't seem too good to me.
How is that any different from any other storage target?
Well,
SCSI storage target has a controller, it has buffers. I'm pretty sure that
they usually
they
allocate
don't.
memory per host.
I don't think so.
Okay.
The size of the memory needs to be sized according to the bandwidth latency product, not according to the number of hosts.
I think I disagree, but okay. And then the second question is, I noticed that you have your NVMe completion queues in host memory. So they're mapped up into host memory, right? How does the offload know when a completion was written?
Okay, so first of all, I don't think that the NVMe device cares where it's mapped. It just knows that it doesn't reside on the NVMe unless you mapped it to the controller buffer of that NVMe, maybe. You could use it for that purpose. The way you know it is that we tell the offload these details. This is the purpose of this backend controller object. Basically, we specify the physical memory address that holds the completion queue. So when you have that parity bit where you detect NVMe completions, the hardware actually pulls that bit and detects the completion just as software would.
I'm just not sure I follow how the offload knows that a drive wrote a completion.
So before we start the offload, we provide the hardware the address of the completion queue.
Okay.
So it directly pulls on that completion
Oh, so
queue.
it has to pull, okay. All right.
Mhm.
Thank you. No.
Guys, can I?
Next.
Yeah.
Okay.